We'll start by looking at your equation sheet. So with your equation sheet, I took some screenshots of all of the torque questions on your equation sheet, which is everything that's in a box in this table. This table, my goal was to help you isolate and identify everything that is, what do I use it for? When do I use it? What does everything mean? And some basic, okay, if this changes like this, how does this other thing change? So rotational equilibrium. Rotational equilibrium, this is Newton's first law, but for rotation. If something is not rotating, that means that the torques are balanced, which is what you looked at in the torque poggle. But it's critical for you to just know this vocab term, rotational equilibrium. They use that phrase a lot. So rotational equilibrium, that's a phrase that they like to use, saying that the counterclockwise torques are equal to the clockwise torques. And convention, just like your unit circle, counterclockwise is positive. It's like the unit circle. So counterclockwise is positive, clockwise is negative. It does kind of feel backwards to those of us who have ever looked at a clock, but it's the unit circle. So that's R1, F1 sine theta 1 plus anything else that's counterclockwise. R2, F2 sine theta, oh, sorry, misprint, 2 plus anything else that's that's clockwise. They are all equal. This is Newton's first. Newton's second law for rotation, instead of sum of the forces, it is now sum of the torques. It doesn't quite feel the same to say, we're just so used to sum of the forces. So it's the sum of the torques. And because it was sum of the forces equals MA, essentially the rotational equivalent of mass is rotational inertia. Or if I have more mass, it's hard to accelerate. If I have a bigger rotational inertia, it's hard to angularly accelerate. Oh, and this equation is y. So, and then alpha is like linear acceleration, but rotational. So it's the same equation. AP gives it to you in the form of alpha is net torque over I, as opposed to net torque is I alpha. The same way that they give you the real Newton's second law is A is net force over mass. It's the exact same way. Alpha is net torque over I. For a single individual torque, that's what you were working on last time, RF sine theta. Rotational inertia. Remember, this is for point masses or for hoops, things that don't touch the axis. If it's mr squared, it doesn't touch the axis. If it does touch the axis, they're going to have to give you more information. Like a parallel axis theorem problem. Which is that second one. To note, if the mass is further, larger I. So it's slower. Mass is further, larger I, so it's slower. It's like my clay on a stick. Or my not edible lollipop. Right, if the mass is close, it accelerates quickly, and I can't really balance it on one finger. But if the mass is far, it accelerates slowly, and you can balance it on one finger. That's why when you balance something on one finger, the mass needs to be far away from you, because large I means small alpha. They ask that question a lot, conceptually. if I make this change to the object and they move the mass further away or closer to, what happens to the angular acceleration? They ask that question a lot. And all you have to do is use this line of logic.
Is that first equation only for it doesn't touch the center axis or like any rotational axis?
Whatever axis it's rotating on. Angular acceleration, this is what we've done the last couple times. Just motion equations, you can find alpha. Because once you find alpha, then you can plug it into the net torque equation. You can use tangential acceleration, any of those, just like we did with motion equations to find A, plug it into Newton's second law. Exactly the same way. All right, let's look at an example problems. So we've got a rod that is attached to a pivot around its center. Rod has a rotational inertia of 2.5 kilogram meter squared around this axis with a length of 40 centimeters. Two masses are hung at the position shown in the diagram. M1 is 0.25 kilograms, M2 is 0.8 kilograms. What is the angular acceleration of the rod after they are hung? So we're looking for alpha. What is the angular acceleration? Well, we have things hanging that will try to make a thing pivot. That is where we're looking at torques. Because right here we have mass 1 exerting a force of gravity, I'll just call it Fg1, downward at that point. And because there's a force at a radius, this makes there be a torque. Over here, mass 2, it's exerting a force of gravity for this mass M2 downward. Oh, this force of gravity of 1 is trying to make it rotate this way. Counterclockwise or clockwise? Counterclockwise, so that's positive. M2, trying to go this way, which is clockwise, that's negative. Okay, what's the angular acceleration after these masses are hung? Sum of the torques equals I alpha. You know you missed me screaming. Sum of the. All right, well, we have a positive torque from torque 1. We have a negative torque from torque 2. I alpha. Well, this is R1 F1 sine theta 1. R2 F2 sine theta 2. Oh, but what are each of these sine thetas? Theta's 90 degrees in each, so sine theta goes away to 1. So we can, and we're multiplying something by 1, we can just forget they exist. So I have R1, 0.18. Force 1, well, that's force of gravity, so M, G. And then R2, 0.1. Force 2, well, that's force of gravity, so M, G. We're told rotational inertia is 2.5. So then here's alpha. And we can plug this into our calculator. 0.18 times 0.25 times 10 minus 0.1, 0.8, 10. And then divide both sides by 2.5. I get negative 0.14. It's alpha, so units are radians per second squared. What does negative sign tell us?
Clockwise.
Clockwise. So that means that mass 2 wins out. Because we weren't sure. It's a bigger mass, but it's closer in. So big F, small r. We weren't sure which one would win. So we did the math and we figured out which one won. Questions so far? All right, that's Newton's second, but in rotation. Let's try Newton's first. A meter stick with negligible mass is hung from the 40 centimeter mark. The forces and directions shown in the picture act on the meter stick. What must the magnitude of the force F4 be to keep the meter stick in rotational equilibrium? A rotational equilibrium. That means positive torques equal negative torques. Just like Newton's first law with forces. Let's figure out what direction all these act in. F1. It's acting up on the left side, so it's trying to make it go clockwise, negative. F2, it's going down on the left, so it's trying to go counterclockwise. F2 is positive. F3, trying to go down and right, which is clockwise, negative. F4 is trying to go up on the right side. That's counterclockwise, positive. So, this means our positive torques equal our negative torques. F2, I'm sorry, not F. Torque 2 plus torque 4 are our positives. They have to equal torque 1 plus torque 3. Those are our negatives. All right, so this is RF sine theta for 2 plus RF sine theta for 4 equals RF sine theta for 1 plus RF sine theta for 3. We have a couple of torques that are perpendicular though. And if they're perpendicular, we can get rid of the sine theta. So that'll be perpendicular 2 and 4. Oh, so that's this whole left side. So 2 and 4. Sine theta goes away because sine of 90 degrees is 1. So we're just multiplying things by 1. For this radius value on all these, we can't use the position. We have to use distance from pivot. Pivot's at 40. So if I look at force 1, it's at 15 centimeters. So what's our distance? 25 centimeters. So that's going to be our radius for force 1. I'll just solve this for all of them. To go from 40 to 20 is 20. To go from 40 to 65 is 25. And then to go from 40 to 90 is 50 Okay, so R2 is 20 centimeters, 0.2 meters. F2 is 25 newtons. Plus, R4 is 50 centimeters, so 0.5 meters. F4, that's what we're asked. What must F4 be to keep it in rotational equilibrium? R1 was 25 centimeters, so 0.25 meters. Force 1 is 20 newtons times sine of, and here's our question, should we use the 30 degrees or should we do 90 minus and do 60 degrees? Well, when it's RF sine theta, it's angle between F and R. Here's our R, here's our F, so it is the 30. And then plus R3 was 25 centimeters as well. Force 35 newtons. Sine theta, and we run into the same question. We get the same answer to use sine of 53 degrees. So when I use my calculator, I'm going to get 0.5 plus 0.5 F4 equals, and then the whole right side on the calculator, 9.5. So then F4, let's subtract 0.5 from both sides, then divide by a half. I get as 18. It's a force, newtons. I've seen questions just like this on the question bank for multiple choice. Usually a multiple choice will just have 3 forces instead of 4 here. But I wanted to give you practice balancing 2 each way.
2 times 25 is 5.
0.2 times 25 is apparently sure 5. Sorry about that. I knew I should have brought my white out. So then 9.5 minus 5, so then 4.5 over 0.5. Okay, force 4, 9 newtons. Thank you for catching me on that. Okay. Hopefully you're seeing it's the same. Everything's just the same. We just have a new equation for torques instead of individual forces. Next problem. Down a uniform beam, length L, mass M, suspended horizontally from a frictionless pivot located at a point 1/4 the length from the left end. Part A, if you read ahead, asks us to draw it anyway, so I'm going to draw it. So we have a uniform beam of length L, mass M, is suspended from a frictionless pivot 1/4 the length from the left end. Mass M1 is hung on the left, mass M2 is hung on the right end, so that the beam remains in rotational equilibrium. When I see that, I'm just going to make myself a note. Sum of the torques is 0. Or you could also do alpha equals 0. All right, same thing we did for Newton's first law. Okay, A, draw a clear free body diagram of the beam, labeling all forces and the locations they act on. So this is what's different about rotational free body diagrams, is it's not just a force on a single dot that they give us. We have to figure out where does that force act. So There's a few. I mean, we've got mass M1 on the left end. So I'm just going to call this force of gravity 1. We've got mass M2 on the right end. So I'll call this force of gravity 2. Then there's two that you haven't really been trained to think of yet. The rod has mass. So, remind me again, where does force of gravity act? Center of mass. Since it is a uniform beam, that means center of mass is in the center of the rod. So we have force of gravity acting on the rod. And then this last one you haven't been trained to think of yet at all, not just a little bit. That's 3 forces down. What keeps this rod up? The pivot. There's a normal force acting on the pivot. But I'm going to make a note on this. The normal force on the pivot exerts torque of 0 Newton meters because it's got a radius of 0. It acts on the pivot, so it has 0 radius. If there's 0 radius, it means 0 torque. So it's a force that's acting on the rod, but there is no torque because it's on the pivot. Okay, a rod can be described as having a rotational inertia, I equals 1/12 ml squared, when rotated around its center of mass. Derive an expression for the rotational inertia of the rod around the pivot point in terms of ml physical constants as appropriate. So you're given I center of mass, but we have an object that's rotating around not the center of mass. This is classic indication of parallel axis theorem. I'm just copying this equation from the equation sheet. So our new rotational inertia, I center of mass, is 1/12 ml squared plus mass of the rod is capital M like they give us. The distance it is away from the center of mass, well, we're told it's 1/4 from the left end, so it's a 1/4 from the center as well. So L over 4 is our distance. (1/12 ml squared plus), and then I'm going to simplify this a little bit because I have a over 4 that's getting squared, which turns into a 1/16 ml squared. Well, if you'll notice, they have a common basis. So if we can do some fraction addition, we can get this all in one term. I don't know if anyone's ever shown you this before, but I'm going to change your life as far as adding fractions goes. 1/12 plus 1/16. I'm just going to do this enter, and it's a decimal. Math. The first one is frac. Turn it into a fraction. 7/48. That's fraction addition without you ever having to do a thing. So I prime is 7/48 ml squared. Because, right, I mean, you could find a common denominator between 12 and 16, which is 48. And you could do all that work by hand, but why? All right, part C. Starting with an expression for rotational equilibrium. Ooh, they tell you where to start. We love it when they do that. Derive an expression for M1 that keeps the beam balanced in terms of capital M, capital L, this is a typo, sorry, it should say M2, and physical constants as appropriate. Starting with an expression for rotational equilibrium. So that's where we have to start. This is going counterclockwise. These two are going clockwise. So positives equal negatives. The torque exerted by mass 1, that's our positive, has to equal the torque exerted by the gravity on the rod plus the torque exerted by mass 2. R, F, sine theta, all for mass 1. R, F, sine theta, all for the rod, plus R, F, sine theta, all for mass 2. Well, they're all perpendicular. So sine theta goes away to 1 for all of them. That's nice. And then every force is just mg, because it's all gravity. So all these forces are force gravity. So radius of mass 1, well, it's a fourth the length from the end, L over 4. Force 1 is m1g. Okay, same thing. Radius of the rod, well, it's from the center of the rod to the pivot, which we've decided previously is a fourth of the length, L over 4. Mass of the rod is the capital M, mg. Plus, and then R2, well, if this is 1/4, this leaves 3/4 L. And then force of gravity is mg for mass m2. And this is where we get to be pretty happy. Is there something in every term? L over 4, L over 4, L over 4. G, G, G. A lot of somethings in every term. So this first term, we're left with just M1 equals. Oh, hey, look, derive an expression for M1. That's our goal anyway, so we won't even have to rearrange. That's gone, just leaves us with capital M plus, this time there's a 3 hanging out, 3 M2. Done. Got one more part to this problem. With masses M1 and M2, the rod is in rotational equilibrium. Now suppose M2 is removed and the beam is released from rest. D1, identify. Remember this command term from AP, identify. It means you don't have to explain in the slightest. It just means identify. The direction of angular acceleration. Oh, sorry, I meant to cut off the second half of this. Sorry about that. Identify the direction of initial angular acceleration. Well, if mass 2 is just removed, then there's no more force 2. So we had some help going clockwise, now we don't. It's going to go the other way. Hopefully that one's more straightforward. Derive an expression for the initial angular acceleration of the rod after M2 is removed in terms of M, L, M1, and physical constants as appropriate. All right. If we're looking for angular acceleration and we've just talked about all these torques going on, a good starting place is sum of the torques equals I alpha. But now for our torques. Because now if we're looking at this picture here, we no longer have mass M2. So there's just positive Fg1, negative gravity from the rod. So positive torque 1, negative the torque of gravity on the rod. Equals I alpha. And we've already kind of done these individual torques of the R, F sine theta, where the sine thetas went away. R, L over 4. F, M1G. And then the sine theta went away. Over here, rod, L over 4. F is mg, but for the rod. But now we need the I, rotational inertia. Oh, did I, for some reason, already have you find that? Yeah, that was part B. 7/48 ml squared. If you're looking closely at this question, this is the last part of the question. So do we need to simplify? Well, we've got to solve for alpha, but once we do that, we don't have to simplify at all. So I'm just going to do it as easily as we can. L over 4 M1G minus L over 4 mg all over 7/48 ml squared. Done. Net torque over I. In case you're curious, the simplified version, I took the time earlier to do it. Just in case you're curious. $12G over 7 times that stuff. You don't have to get that. You can stop right here. All right, last one. Two concentric pulleys are hung with masses hanging from opposite sides as shown in the picture. Masses are hung from strings of negligible mass that are wound around the respective parts of the pulley. The pulley's masses system is held at rest. Inner pulley has rotational inertia of 2 kilogram time meter squared. Outer rotational inertia 6. System is released from rest. What is the angular acceleration of the system? Well, we want angular acceleration. We've got things hanging from something that can rotate. Sum of the torques. All right, this R1 is trying to make us go clockwise, so that's negative. This R2 is trying to make us go counterclockwise, so that's positive. So torque 2 minus torque 1 equals I alpha. if we look at the sine theta of these, theta's at 90 degrees. So the sine theta part of RF sine theta is going to go away. So torque 2, R, F is mg. So 1.2 times 10. And then sine theta goes away. Torque 1 is R, 0.3 F, 3 times 10, so mg. Sine theta goes away. Well, if you look closely at our equation sheet, they tell you it's I, rotational inertia of the system. In this problem, you're given the rotational inertia of each pulley one at a time. Just means we have to add them together, 2 and 6, because both are rotating, add them together. I, alpha. And if you solve through for this, your calculator should spit out negative 0.525 alpha, so units, radians per second squared. Remind me again, what does this negative sign mean? Clockwise. What is the linear velocity of the 3 kilogram mass 2 seconds after being released from rest? Oh, linear. Linear velocity. So now we're dealing with V instead of omega. Release from rest. So V naught is 0. We're asked for V final. We're given time. Oh, so if we can get A, then we can do this. If we can get A, we can do this. Well, we have alpha, and we have an equation for tangential acceleration being equal to R alpha. We're given 2 different radii, so we just have to look at which mass we're asked about. 3 kilogram mass, well, it's attached to R1, so 0.3. Alpha, 0.525. So our tangential acceleration will be negative 1.575. We're back to normal acceleration, meters per second squared. Now we can use our acceleration for our motion equation. V final is V initial plus AT. That's our regular normal motion equation. V initial was 0, A 1.575, T is 2. So negative 3.15 meters per second. And again, this negative sign is similar kind of a thing. It means it's with clockwise. And it's going down. Yeah.
0.3 times 0.525 is 0.157.
Oh. My decimal places are all out of whack today. 0.1525. Thanks for catching me. 0.1575. 0.1575, which means 0.315. Last part. There's another typo on this. It says quantitatively. Sorry, I meant qualitatively. Can you tell I was typing this when I should have been sleeping? Qualitatively. Sketch the linear velocity time graph. So the 3 kilogram mass is removed. Sketch the velocity time graph of the remaining 1.2 kilogram mass after it's been released from rest. Velocity time. Velocity is in meters per second, time is in seconds. Well, will it, if we do all this stuff again, but now we just don't have torque 2? I'm sorry, now we don't have torque 1. We still have torque 2. It'll still have some angular acceleration alpha, which means it'll have some linear acceleration A. What does a VT graph look like if it's accelerating from rest? Boop. VT graph of an object that's accelerating. Motion graphs still apply in rotation. Okay, and that's it.